Good morning. Our first speaker this morning is Javier López. I am especially happy and especially proud that Javier is here because Javier was a former researcher at my research group, and he did his PhD under my supervision. After completing the PhD, he has been a postdoc researcher at CERN in Switzerland, and he is really an expert in compiler technology, much more than I could ever be. So it's a pleasure to have him here, especially because he's going to talk to something that not everybody is familiar with. I mean, when you think about C++, you think about a compiler that translates into a binary, but nothing in the standard prevents you to have a C++ implementation that is an interpreter. And you may say, okay, but I want C++ for performance. Interpreter is not a good thing. Now, there are a number of use cases where having a C++ interpreter is quite useful. Just a question, how many of you have ever heard of the Cling interpreter? Good. How many of you have used the Cling interpreter? Good. Okay. Yeah, you see? So I leave you with Javier. Javier, thank you very much for coming.
Sure. Good morning, everybody. Thank you for the kind words, Jose Daniel. So yeah, today, well, let me start the STD chrono. Well, it's a regular chrono on my mobile. So today we are going to talk about interpreted C++, as Jose Daniel said. I'm sure that whenever you think of C++, you can think a lot of words appear in your head, but I'm sure interpreted it's not among them. So today, basically we are going to revisit opportunities to interpret C++. But first, let me briefly introduce myself, although Jose Daniel did a very great job. So I was a former student here at this same university where I did the PhD 4 years ago already. I finished it. And as part of the PhD, I collaborated with the root team at CERN in the development of the Cling interpreter. But also I had some previous experience with Clang because I was involved in developing a prototype implementation of the C++ contracts feature on a fork of Clang. And basically, after finishing the PhD, as Jose Daniel mentioned, I went to CERN for 3 years, where I collaborated with the root team, not only in Cling, but also in some other projects under the root umbrella. Currently, I'm working for Simperium as a compiler engineer, working in a solution that allows you to lift the binary from ARM64 to an intermediate representation and apply obfuscations and then lower it down again to machine code. So that's all for the introduction. This is the agenda for this talk. I'm going to start with a brief introduction to interpreted C++, and then we are going to go through the foundations that make this possible. This is going to be a quite technical talk. And later I will talk about Cling itself, and I will end this presentation with some closing remarks. So let's start. To be honest, I wanted to start this talk with a kind of spoiler. So how would interpreted C++ look like? So for example, you can, let me perhaps point at this. You can define a function template, takes a couple of arguments, and then returns the sum of them. And you can instantiate it for integer and actually print the result. But you can also instantiate it for any other type, in this case, std string. But also you can do abominations, such as this one, that are not ISO C++ standards compliant. So previously we had defined std, f to be a function template, and now we are redefining f to be a std vector of int. And if we ask the interpreter what is f, it tells me that it's a std vector. So this is what you would expect from an interpreter, right? So why bothering to actually interpret C++? As Jose Daniel briefly mentioned before, there is quite some use cases to allow and permit this. And to start with, there is many languages which started being developed at least in the first stage to not be interpreted, to be compiled. This is, for example, the case of C#, and they at some point incorporated a REPL, a read eval print loop, so that it's basically a prompt where you can type things and interpret it on the go. But it also aids a lot in regards to learning the language. You can try things out and see the results as you go. You can do iterative prototyping and exploratory programming. You can write external scripts that you feed to the interpreter and you get the results as many times as you want. And then when you're happy, you can actually compile them using a regular compiler to squeeze all the performance out of it. And also, even if it's not mentioned here, there is a very important use case, which is having dynamic bindings. So think of it this way. If you have a C++ library and you want to use it from Python, for example, basically you make use of a static binding generator. But if there are either class or function templates involved, you can only generate bindings for some of the instantiations of those templates. If you want to generate bindings for some specific instantiation that it's only known at runtime from the Python side, you cannot do it. So JIT'ing that code at runtime would be the ideal solution, and we can do that. So what is the current state of affairs? Basically, Cling is currently built on top of Clang and LLVM 13, which enables us to support C++20. We have CUDA support. We allow loading an external library, be it a cert object on Unix or DLL on Windows, and you can access its symbols and call a function, etc. We also support debugging and profiling the code that has been JIT'ed. We can undo steps. So if you type some input lines to the interpreter, you can undo them and then do some other stuff on top. And there is also some additional features such as protection against invalid memory accesses. For example, the referencing a pointer that points to God knows where and whatnot. But also some other features that one would expect from an interpreter, even if they are not ISO C++ compliant, such as top-level statements. You would expect that from an interpreter, right? To be able to type a statement and get the result out of it, even if the ISO C++ tells you that the translation unit is just a collection of declarations, right? So you can print the result of expression evaluation as well. We can do auto keyword synthetizing. So if we have this line here, foo equals 42.0, basically if foo is not defined before, we can make it equivalent as auto foo equals whatever. And we also support predefining entities, as we saw before. So yeah, let's get into the gritty details on how these work. Let's start by the foundations of it. So those of you who are in the compilers area, I don't know how many of you, please raise your hands. Anybody working here in compilers? Well, it's not a popular area, I would say. Okay, fine, cool. So as you might have guessed, we are based on LLVM and Clang, as I said before. For those of you who are not in the compilers area, I will briefly introduce LLVM and Clang. Basically, LLVM gives all the infrastructure that we require to build a compiler. That is basic data structures, intermediate representation that we can then lower down to machine code of several targets, for example, x86, ARM, ARM64, and whatnot. It allows us to pass some machine-dependent or machine-independent optimization passes, and it allows us to generate debug information and much more. This is, well, more or less a simplistic anatomy of a compiler. basically we can distinguish two parts, what we call the compiler frontend and the compiler backend. The compiler frontend basically deals with all aspects of processing the apologies, I have a bit of a cold. So all aspects that involve processing of the source language, that is C++ in this case. So that's lexical analysis, syntactic analysis, and semantic analysis to be able to finally generate what we call an abstract syntax tree that represents the grammatical structure of the program together with some annotations that has been done as part of type validation and type deduction and whatnot. And it basically finished with generating this intermediate representation. The compiler backend, in turn, basically gets this intermediate representation, applies some optimizations, and generates code for a specific target architecture. So this intermediate representation, in the case of LLVM, it comes with its own intermediate representation, which is simply called LLVM IR. You might not have guessed it. It has three different representations: the in-memory structures, an assembly-like, plain text, dump, and the serialized form that we call the bit code. So let's play a bit to try to build the LLVM IR for a simple function. Here, this is the first slide with code. Here we basically are creating a LLVM module, which you can think of it as a collection of global symbols that might be linked together with some other modules as well. And basically, in this module, we are defining a function called func, which takes a couple of 32-bit integers and returns a 32-bit integer. There is a single basic block. A basic block, by the way, is a sequence of instructions that run from beginning to end, which we call entry, and we add a couple of instructions. One add instruction that adds together the two values for the function arguments, and a read instruction that returns the added value. And then we ask LLVM to print the module. This is what we get. This is the plain text dump for the module, which represents exactly what we wanted. So the fun fact here is not that. The fun fact is that LLVM can actually JIT this intermediate representation to machine code of the current target. So basically, we initialize output for the native target. Here, basically, you get you have the code for what we had in the previous slide, and we tell LLVM to build an execution engine that is of type JIT, that is just-in-time compile, out of the module that we created. And then we ask for the address of the func function, and then we cast it. Apologies for the C-style cast, but I thought it was shorter for the slide, basically. We cast it to the function type, basically that corresponds to what we defined in the IR, and then we call it. And yes, this prints what you would expect, 49. Clang, on the other side, is the front-end counterpart. So Clang basically parses C, C++, and Objective-C, and generates this AST that we briefly mentioned. We are going to make a brief journey now around these concepts. And it ends basically generating the IR representation that, and from there, LLVM takes over. So basically, we have this simple source program. Note that to avoid adding too many declarations because of basically including some external header file, I just declared put-s manually here as an external linkage symbol, and then we call it with some string. So if you basically run Clang as follows, using this command line here, you get the AST representation. As I briefly mentioned before, the AST is basically a tree that represents the grammatical structures that you find after parsing the input program. So you can clearly differentiate the two function declarations, the one for put-s, the one for main. There is a call to put-s, providing the string literal hello world, and you can see a lot of stuff, basically the types of each of the entities, some implicit stuff such as array to pointer decays and source location and whatnot, a lot of unimportant stuff that we are going to skip for now. Next stage would be to actually generate this intermediate representation for LLVM. And this is the more or less the step for what is important. Basically, I removed some unimportant stuff. And you can clearly differentiate the declaration for main that calls put s, and put s is defined as some external symbol and whatnot. Here we have the definition for the target triple for the current architecture, and the data layout that defines the sizes of all the types. What is the size of an integer? What is the size of a long? What is the size of a pointer? And all this stuff. So most of you, I think you all think of Clang as basically a compiler that they can invoke from the command line. That's cool, but that's actually what we call the Clang driver. There is also libclang CPP, and whatnot that you can use as a library. So you can integrate all the parsing that Clang does in your own program. That's cool. And that's what makes Cling possible. So we are now going to talk about the Cling interpreter itself. So basically, all what Cling does can be seen as a pipeline for each input line, unless the input comes from an output file, in which case we optimize some of the stuff. But if you type things on the prompt, basically, it runs this pipeline for all input lines. So let's start with a simple example, calling again put s. So first stage would be to wrap top-level statements into some wrapper function, because top-level statements doesn't exist in ISO C++. I mean, an ISO C++ translation unit is basically a collection of top-level declarations, not top-level statements. So basically, you would have to wrap these into some wrapper function so that the code is not ill-formed. So basically, we detect whether some of the structures or constructions in the input line need to be wrapped in, or partially wrapped into a wrapper function. Next, we invoke Clang as a library, as I talked before. We basically tell Clang, here you have this fragment of code, please parse it, and then it will basically make the AST grow incrementally, and this is the delta that has been added. It's a bit too small, but I wanted it to fit in this slide. Basically, it's the same AST fragment that you saw before. Then we might apply some transformations to the AST deltas that have been added to the final AST. So that basically enables us to support some additional features, such as this symbol redefinition thing, the invalid memory dereferencing, and etc., etc. Later, we ask Clang, okay, can you please generate the intermediate representation for this? Can you code gen this? And we basically hook into this stage so that we get a view of everything that gets emitted to the final module. And basically here you can see the string literal hello world together with the wrapper function and the call to put s. And finally, if the transaction, we will see it later, but we call this a transaction. If the thing had a wrapper function, we get the function pointer and we call it, as we saw before in the foundation section. There is a lot of details that we have to take care. I'm just trying to summarize it and to make it easy to understand for the audience, but there is a lot of things that we have to take care of because when there is implicit template instantiations, for example, they are deferred until the end of the translation unit is reached. So for all these to be emitted, we have to somehow force the end of the translation unit. So we do that. There is also some linking and resolution of relocations also involved in case you use some external symbols and whatnot. So this gets a bit complex. So it's not as easy as it seems here. So let me briefly introduce the concept of transaction. Basically, we saw that the AST is built incrementally, and all these declarations that have been parsed as a whole and become a delta to the AST, we call it a transaction. So it involves user-provided declarations, so implicit template instantiations, and deserialized declarations from a C++ module. also, although I have not mentioned it here, it also includes some macro definitions that you might have also defined. The important thing here is that we add those deltas, those become part of a transaction, and you can revert transactions. So you can delete declarations from the AST and make the backend side, that is LLVM, to forget about the emitted symbols that match the corresponding deltas on the AST. So let's talk about extensions briefly, because I'm running almost out of time. So most of the extensions for Cling are implemented as AST transformer. Currently, we have support for the auto keyword synthetizing, as we saw before. So in case you type, what is the pointer here? In case you type foobar equals something something, if foobar is not defined, basically we synthesize the auto keyword and you get auto foobar equals whatever initialization value. There is protection for invalid accesses to memory. For example, here I have this random hex value that is casted to a pointer to integer, and then we dereference it and assign it. Of course, there is little chances of this address being valid, so we get this kind of message out of the interpreter, because remember that we are basically JITing all the code that we JIT. It's basically outputted on the virtual address space of the process, of the interpreter process, and any call that we do is also in the context of the process. So if we don't protect memory accesses this way, you would crash the interpreter. There is also shadowing of definitions, as we saw before, so you can provide new definition for a symbol. In this case, we declare a variable of type int, and then that is called foobar, and then we redefine foobar to be a function that returns a string, and then you can actually call it and get the value printing. As I briefly mentioned in the introduction, Cling also works with debuggers and profilers. We have support for the well-known debuggers such as DDB and LLDB, and we are able to also integrate well with the perf, Linux perf utility, so that, for example, you can set a breakpoint and do single stepping on your code, and yeah, you can get nice profiling information with perf. I'm going to skip. Later, if you have questions, please do not hesitate to ask. So what is the future of this? Basically, the project is now in maintenance mode. That means that we are not going to do any further development. We are just doing bug fixes and whatnot. And basically, this proved to work perfectly for the use cases of the root project at CERN, which are, I mean, it's a pretty big project that is used by the physics community. So we thought, okay, this is quite useful, so let's upstream the foundations that make it possible back to the LLVM community, so that everybody can get benefit out of it, and that it's easier also to maintain in the long term. So there is clang-repl, which is the project that came out of basically upstreaming all the foundations of Cling. You can try it. It's basically part of current versions of LLVM. So most likely, if you have LLVM installed locally, you already have it. So thanks, Vasil Vasilev, for taking care of this. And yeah, just to make a brief mention, the management of top-level statements that we saw before works really differently in clang-repl. So it's much more sophisticated. We don't need this kind of artificial wrappers that we created. So let's wrap it up. Cling basically enables you to do C++ compilation and actually just-in-time compiling. That would not be possible otherwise without the power of LLVM and Clang. There is also convenient integration with Jupyter notebooks. We didn't talk about it before in the talk because we didn't have time, but you can use it from a Jupyter notebook, and I encourage you to actually try it. For the curious of you, I would like to mention a couple of side projects. There is CPPYY and libinterop, which enables interoperability with other languages, such as Python. So we can do crazy things, such as injecting the declaration for some random class that you would like to inject. And you can actually instantiate it from the Python side on the fly. Or even crazier, you can actually instantiate the STD vector of that type that you injected. This is the URL for the project, just in case you are interested and curious, and try it. And thank you all for listening.
Thank you, Javier. So, questions? Oh.
Hello.
Thanks for the talk. Hello. Is it possible, I assuming it is, to include something using clean? I mean, hashtag include whatever.
Yes.
Can you then access somehow the AST or that you get from that include?
Yes.
Okay, so it is possible to actually see what is being included and
yes,
and call that functions, even if they reside in a shared library or in a library?
We just parse the external header.
Yeah.
You do bound include whatever, and then we have what we call the meta commands that start with a dot. So you can type dot something something at the interpreter prompt, and there is a meta command that allows you to print the AST. So you can view, you can actually view the AST.
Okay, that's interesting. Thank you.
You're welcome.
Thank you. Any other question? Well, Javier will be around, so probably during the coffee break or so, you can interact with him.
Great.
So, thank you. Thank you very much.